4, we're going to take a look at the normal approximation to the binomial distribution. Basically, what we're going to look at is under certain guidelines and certain criteria, we're able to use the properties of a binomial distribution, and we're going to be able to sub them into a normal approximation. And of course, when we talk about normal, we talk about z equals x minus mu over sigma, right? And use that, the area under the curve, the bell curve. And when we talk about normal distribution, or sorry, binomial distribution, we can recall down here that mu equals np and sigma equals npq. Okay, so this just reads, the normal distribution is a continuous distribution. We know that. The issue is that in real life, there are many, there's many data, there's many situations where we can't use continuous data, but instead it's discrete data. So as long as discrete data is modeled by a binomial probability distribution, and the sample size is big enough, this is the key right here, sample size being big enough, and that's actually what we're going to check. Then we're able to use the normal approximation because it's a good approximation. And then that just makes everything easier. So here's your check. When we multiply NP, it must be greater than 5. When we multiply NQ, it must be greater than 5. If both of those hold, we're able to use the normal approximation. So let's try the first example. Okay, a bank found that 21% of its loans to new small businesses become delinquent. So that's like a bad loan when people don't pay it back. If 150, so probability equals 0.21, and then probability of Q, and P is delinquent. Probability of Q, it's going to be 1 minus the 0.21, which gives us 0.79. There we go, 0.79. Okay, if 150 small businesses are selected, so n equals 150, randomly from the bank's files, what is the probability that at least 50 of them are delinquent? Well, first, we know that this is a probability distribution because it's we have P, Q, and N. There's a set number of trials, and we have two outcomes. We have success, which is delinquent, and then we have failure, which is like a good loan. So let's check if we're able to actually use the binomial approximation or the normal approximation. Okay, so let's check NP and NQ. So if you look here, I put NP is greater than 5, and I put a little question mark above it. So 150 times 0.21, is that greater than 5? Well, we get 150 times 0.21, 31.5. And that's greater than 5, so we're good over here. Now, 150 times 0.79, is that greater than 5? Okay, it's 118. It's greater than 5. So by doing this check, and you have to show this check in your work, we're able to use the normal approximation. Now, here's the actual question. What is the probability that x is greater than or equal to 50? Okay, so we must remember, because this is discrete data, you might want to make a note, discrete data, we need to gap or take into account the error for the exact number of 50. So we use plus minus 0.5. And remember, I mean, if these data, the discrete data that we're dealing with already has one decimal, then you move this to the next decimal and to the next decimal, and you keep going until it's satisfied. Okay, so pretty much instead of saying when x is greater or equal to 50, we're going to actually say when x is greater than or equal to 49.5. There we go. So instead of that, because that would be continuous. Now, we have z-score equals x minus mu over sigma. So our x is 49.5. Our mu, well, we know from up here, mu equals np. we solved NP, it's 31.5. Okay, and I'll actually list these. So mu equals 31.5. Now, sigma is NPQ. So take that 31.5, which is like your NP, multiply it by 0.79, and then root it. And I get 4.98. Let's just round to 5. Nice, beautiful number. Okay. Now let's actually solve this. 49.5 minus 31.5 divided by 5. I get 3.6. So if you think about our distribution, we think about the average, which we get 31.5, and then gapping it by 5 each time. I mean, 99.7% of the data is going to lie within three standard deviations away from the mean, right? So this is sigma. So if we have the number 3.6 as our z-score, that's 3.6 standard deviations away from the mean. This is almost going to be 0. So let's actually take a look at our z-score table. So let's take a look at 3.6, okay? So you know what? 3.6, not even on, because these get to 99.98%. So it's almost a 0% chance. And that's totally fine, as long as it makes sense, okay? So therefore, there is almost, because nothing's actually a 0% chance. Well, almost nothing. So there's almost 0% chance that at least 50 will be delinquent. Okay?